Good evening. This paper is going to be discussing the uncertainty introduced by flood frequency analysis in projections for changes in flood magnitudes under a future climate in Norway. This paper was researched by Deborah Lawrence, who works for the Norwegian Water Resources and Energy Directorate in Oslo as part of the hydrological modeling section. Today, we're going to discuss the study goals of the paper by Deborah Lawrence, and then move on to defining some of the terms and concepts to be able to work through this paper. We're going to review the methods of the research and the results that it found, and discuss some of the conclusions that arose from that. Finally, we're going to discuss future work suggested by the author and myself, and assess what, in my opinion, and the author's opinion, are the pros and cons of this paper. The goal of this study was to investigate the uncertainty introduced by standard methods for statistical flood frequency estimation when applied to an ensemble of hydrological projections. This goal is broken out into four main questions that the author wants to answer. First, do extreme value distributions with a shape parameter give significantly different estimates for projected changes in higher flood quantiles? Do extreme value distributions with a shape parameter give a better fit to the extreme value series? What is the average contribution of flood frequency estimation to the range of ensemble estimates for changes in higher flood quantiles? And how do the average extreme value distribution parameters change under a future climate? And can this change be related to flood generating processes? So keeping those questions in mind, we're going to define some of the concepts and terms that this paper goes into. Some of the challenges of getting hydrological projections, including climate change, is that there is a local bias, especially when there's varying forms of topography, even within the same country, such as Norway. The catchments that they're going to analyze vary widely in their properties. When they're getting climate projections, there exists a reliability of downscaling, especially when larger timeframes need to be turned into smaller timeframes, such as yearly to monthly to daily, for the use of hydrological models. When there are changing conditions, there is a challenge of the suitability of the model and of the model's parametrization. And finally, given that there are more than one greenhouse gas concentration pathways, which one is the most suitable to use? And these are all going to be addressed in this paper. When it comes to a statistical distribution, there is a parameter called the shape value, and this describes the skewedness of the data. And this paper, because it looks at extreme values, which flooding is an extreme value, it's going to compare extreme value distributions with and without this shape value. In prior research, extreme value analysis included assumptions such as extreme events being independent, identically distributed, and well stationary. And in the real world, this is not the case. And it's a big topic in research to see, as climate changes, how these effects are laying out with the non-stationary attributes. So the applications, especially considering this specific to this paper in Norway, is a risk to housing and flood control structures, as well as assessing the risk to hydropower reservoirs. In a climate such as Norway, they have to compare the contribution of snowmelt versus rainfall. In snowmelt dominated regions, we're already seeing a pattern of earlier flooding and less magnitude flooding in our present time series already. However, there aren't many things that we're able to currently lay down and understand, which is why we want to model them. In areas where there is snow melt and rainfall that are both contributing to flooding, it's difficult to model this due to competing effects. And it's not helpful that there's no specific correlation of flood magnitude and changes in precipitation due to topography, etc. So this paper is going to look at many different catchments in order to analyze that. Past work with extreme value distribution, which is EVD here, includes a distribution chosen based on factors including characteristic of the basins and the lengths of time compared, which in this case is going to be 30-year comparison sections, as was done in papers prior. The design floods in Norway, as well as other academic work, uses what is called a Gumbel distribution, which has two parameters. And the advantages of this distribution are that it's more stable than the next ones. There's another pair of distributions, both of which have three parameters, called the generalized extreme value and the generalized Pareto. And these have the advantage of being more reliable. That extra parameter helps with that. So moving on to the methods, this paper uses the ensemble method, which is where they run multiple realization of the models and the climate inputs and provide a comparison. This is due to the fact that the climate change predictions are varying. This ensemble method will be comparing the climate model as well as analyzing different ways of processing the climate model. And it's also comparing different runs of the hydrological model and the parametrizations of the hydrological model. The novelty of this paper is that it analyzes uncertainty from creating estimates for extreme flooding quantiles. And this has not been studied much before. However, the paper did mention prior work for catchments in Poland and the United Kingdom. So elsewhere in Europe, but maybe not as snowy as Norway. What we're analyzing are the severity of the floods for given return periods. This is pretty application driven. They want to look at the 10-year return period flood, the 100-year return period flood, the 200-year return period flood, which in Norway is used for flood hazard mapping for land use planning. We would use a 100-year flood here in the United States for determining floodplains and insurance risks and FEMA flood insurance requirements. And the 1,000-year flood, finally, the 1,000-year flood, which in Norway is used for the design flood for analyzing dam safety. They chose 115 catchments across Norway, and the catchments follow the general characteristics here. They vary in size as well as their different flow regimes. They have little to no stream flow regulation. So these are all likely upstream of dams, but they do not have upstream regulation themselves, which helps when analyzing floods. They chose 115 catchments with varying topographic conditions and landscape types. And they chose them with various climate effects for moderate versus high temperature increases. This is due to different catchments will experience different precipitation increase ranges, as well as seasonality, in addition to snow storage. So they wanted to cover a variety of bases and look for those patterns. And we can see some of that here. Norway is a long, thin country, and they discuss the different catchment characteristics by region below. Up north, they tend to have a lot less runoff, a lot less snow, a lot fewer days above 0 degrees in the winter, which winter in Norway is half the year, it's 182 days. So for example, Finnmark and Troms, only 27 days of that half a year are above freezing. The elevation is a little bit more consistent. Some of the average elevation in the west is a bit higher than the average elevation up north, as well as in the west, there's a quite steeper due to the topography. But what really we want to stick out here, all the way the column to the right, is the percentage of rainfall. And so they want to define the flood as coming primarily from rainfall or from snowfall, and it's a percentage. And then whatever's not in the percentage of rainfall is in the snowfall. So when it says 32% from rainfall, that means it's 68% from snowfall. 60% from rainfall will be 40% from snowfall. So I want to highlight the column on the right. In the south, it's 84%. The vast majority of the flooding is due to rainfall. And up north, that's very snow driven. So keeping on with the methods here, they did look at different flood regimes, as I just explained. The snow dominated, the rainfall dominated, and many of these catchments are mixed. There is not one single way that they're forming floods. Both snow and rain are both very important for forming the floods. The climate model used is called Eurocordex, and they did 10 runs for each of these catchments for each of various scenarios. The resolution used is 12 kilometers. There are several different RCP values, including 4.5 for moderate increases in temperature, but because of the national guidance of Norway, they decided to use RCP 8.5, which is the high level of warming. And that's what they're going to be using for this paper. They're not going to be comparing that to 4.5. The reference period, so the present condition, 1971 to 2000, and then the future period is going to be 100 years later, 2071 to 2100. So in order to provide more reliable findings, they did bias adjustments, including two different methods for the precipitation time series. These bias adjustment methods are the imperial quantile method and the double gamma method. And they do run both of these, as we'll see when they're building up their ensemble. The temperature time series is bias adjusted using the normal distribution. And the paper points out that prior work has shown that the normal distribution is suitable for this bias adjustment. And they did want to point out that the corrections to bias were implemented after a trend removal process was put in place to ensure that climate trends were not impacted by bias correction. These are still not time varying parameters or anything like that, but they do recognize that climate is changing even just in 30 years. And they want to be able to make sure that they're not removing that trend with a bias adjustment. So that's the climate model used. The hydrological model used is called HBV. And in order to create their ensemble, they picked many, many instances with different parametrizations. And they calibrated using the observed data, and their qualifier for what was an okay parametrization is a Nash-Sutcliffe efficiency of at least 0.5, which I've talked about that in another presentation. And they did want to do a little note here, even though the model performs well with both, they say it performs better with snowpack-driven regime than the rainfall-driven regime. And they say that's due to additional variance of the rainfall time series because it varies a lot more than the snowpack, which just builds up and melts generally. The frequency analysis methods, they did the three methods. Prior work has already established the two-parameter Gumbel method due to its relative robustness. However, this does not account for skewness, which is of interest in climate change scenarios. The other two frequency analysis methods are the three-parameter GEV and the three-parameter GP. In order to compare these and make sure that they're acceptable, they use the Anderson-Darling test for the goodness of fit comparison. In order to create the ensemble and put all those steps together, 10 climate projections, 2 bias correction procedures, 25 model parameter sets from 125 that were looked at, the 25 that were the best were chosen based on the HSE. Multiply all that, 500 simulations. And so they did 100 samples per catchment 500 times. So each of the 115 catchments has 50,000 samples. So if you multiply all that, the whole study has 5 million plus, which is quite a few samples. And they usually discuss these when we're looking at our results as means and medians. And a big part of the methods here is decomposing the variance and figuring out where the variance is coming from. And they looked at 4 things, 3 of them, plus the interaction terms between them. So they looked at the variance in terms of climate data, in terms of the hydrological model parameterization, in terms of the flood frequency analysis, and then the interactions between those 3 items. So there's 3 different interactions, as well as the interaction of all 3. So now we can go into the results. And the first step, because it is useful for risk analysis, is comparison of the 200-year flood between flood frequency analysis methods. So this is where they're comparing the Gumbel to the GP to the GEV. And they found that these 3 methods generally align with where in space in the country of Norway the smaller increases and the larger increases in flooding are occurring. However, the three parameter methods, which are generalized Pareto and generalized extreme value, show stronger increases in the magnitude of the 200-year flood. In general, northern, middle, and then the inland parts of southern Norway are seeing less increases and even some with decreases in the magnitude of the 200-year flood. And in western and coastal regions in southern Norway, we see a larger increase in the modeled flooding magnitude. And here we can see that laid out. The small green circles are where the 200-year flood is actually projected to get less severe. The small blue circles are where it's becoming only a little bit more severe. And then the other circles, blue, navy, and then purple, are showing increasingly severe 200-year floods. And we see they generally follow the same pattern of where in the country, which is good for validating each other. But the two graphs on the right, which are the three parameter estimations, the generalized extreme value, and the generalized Pareto value, are showing more extreme flooding. Next, we want to compare based on the contribution of rainfall versus snowfall. So on the horizontal axis is the percent change in the 200-year flood magnitude from the present day to the future day. And then in the vertical axis is the contribution of rainfall to flooding. So all the way at the bottom, those would be the coldest areas. They are mostly snowfall. All the way at the top is it says 10, but it should say 100. That's where it's mostly flooding, not much rain at all. And the different colors signify just the different instances of the generalized extreme value and the generalized Pareto and the Gumbel. So the takeaway here is that the ones with significant rainfall, which are the ones in the top half, they're all showing increased flood severity for the 200-year flood. Down at the bottom half are where there's significant snowfall. Only some show the decreased flood severity on the bottom left, and then some show increased flood severity, and then some show very significantly increased flood severity. So we're seeing a lot of difference there with the snowpack regions. Next, we want to look at the analysis of the decomposition of the variance. They looked on it a few ways. They looked at it first based on the year, so the return period. The 10-year return period, so the most likely floods in a given year. Each of these three frequency analysis methods showed about the same level of variance. And then compared to the 100-year, the three-term methods, so the GP and the GP or GEV, show a significantly higher variance than the two-term Gumbel frequency analysis method. And then you go to the 1,000-year flood, and this is the one used for dams and reservoirs. Those methods show a much higher variance than the two-term method. And let me skip ahead with each of these just to go over that. So that's the one on the top here, section A. We can see that for the GEV and the GP, there's a lot higher, significantly higher variance when you go up in the significance of the flood. And the GP has less variance than GEV. And then the Gumbel doesn't have as much variance as either one of them. Second, going into the source of the variance, and this is the different colors here. It's monochrome colors. The climate data is a strong source for all of them of variance, but less for longer return periods in comparison to the other sources of variance. The frequency analysis method is a strong source for all, so which method we're using gives quite a bit of variance. The hydrological model is a pretty low source of variance for all the instances. And then we have the interactions between those three properties. The interactions are a strong source for longer return periods. And then as far as which interactions are most impactful, the interactions of the frequencies analysis method and the climate model are significant. Let's jump back in here. You can see in the middle graph here, the black part is the climate model. And this is more than half of the variance for the Gumbel, and it's still a pretty significant part for the other two frequency analysis methods. In the other two methods, we're starting to see, as the year goes up, the interactions become more of a source of variance. That's that third row there, the interaction terms. We can see that for both the GEV and the GPD, the CLFFA, so that's climate interacting with the frequency analysis method, is a big most of that variance from interaction terms. And then the last thing here is that in order to provide a goodness of fit test, the GP performed the best, followed by the GEV, followed by the Gumbel. The last thing here for the results is that we want to look at and compare the parameters for the frequency analysis. So there's 3 parameters shown here, but you can see on the right, the shape parameter does not have any dots for the Gumbel method. That's because the Gumbel method doesn't have it. The parameter changes are more apparent and varied, more variance sideways for the snowfall dominated regions. And then the location and scale parameters are increasing with time, while the shape parameter slightly decreases is a general pattern. What these parameters look into specifically is that the location parameter is the location of the mean. And so we can see in the leftmost graph there's a general trend, especially in the rainfall dominated regions, that the mean would be higher, which makes sense given that, we're seeing increased severity of the 200-year flood in the future. The scale factor tends to expand and contract the extremes. And again, we're seeing an expansion there. We're seeing more extremes with climate change, which is something we would expect, but this is a little less easy to see. And then we want to add the shape factor in order to have a better analysis of climate risk. And this affects the skewness. And as we can see on the right, we're not seeing the same pattern that we were seeing with the others. We're seeing that there is a bit less skewness for many of the extremely rainfall and extremely snowfall dominated regions. But for some, not all, but some of the mixed regime, we're seeing more skewness. And that's what's in the middle, that bulge out on the rightmost graph here. And so that is able to help the climate scientists and people analyzing this study catchment to be able to focus on risk. This slide, we want to go over the main takeaways and conclusions and how they're discussed. So in summary, in the snow-dominated regions, we're seeing some decreases in the 200-year flood magnitude, along with some increases. And these increases are actually the most extreme. In the rainfall-dominated regions, we're seeing increases in the magnitude of the 200-year flood. They have also observed the variable responses in other studies in Alpine Europe and in Western North America, which I'm glad they pointed that out. Looking at the variance of the methods, the GEV and the GP have more variance in the 100 and especially in the 1,000-year events than the Gumbel. The GP performs better on the goodness of fit. The paper author says this is likely due to the larger number of available observations because of the way that the generalized Pareto runs. And what they really wanted to get to is the recommendations or general recommendations for updating the design criteria. So Norway currently uses a climate change design flood increase allowances of 0%, 20%, or 40%. And this depends on the region, but this is based on prior Gumbel distribution work. This paper is suggesting through the GEV and the GP analysis that the design flood allowances may be actually too small and that larger values may want to be used to be more conservative, given that the nature of climate change and how the frequency was analyzed here. For the 200-year floods, for the land use analysis, they might want to see a small increase in the design flood, but as we saw earlier, it's the 1,000-year that has a very marked increase in the potential flooding magnitude And then they suggesting possibly more drastic updates be considered to be conservative. Again, prior work was completed with the Gumbel distribution, but if they do want to, in Norway, switch over to a 3-parameter frequency analysis, the GP performed better for the goodness of fit tests. So the author has suggested several items for future work. One of the limitations of this paper is that it did not use time varying parameters. Especially if they want to use a longer analysis period. 30 years was used here, but time varying parameters allow for a longer analysis period and digging deeper into climate change. However, they say that if they are going to be adding parameters, especially shape parameters, they should include investigation into the real world processes instead of just fitting additional parameters. Just adding more parameters, as I discussed in a paper a few months ago, isn't always the best thing, can lead to over calibrated models. You want to be able to get the real world knowledge in there. That being said, if we're providing a regional solution to the design flood event for an ungauged catchment, we want to incorporate local features and expert knowledge, but not simply rely on that. We also want to have a well-established regional model. My suggestions for future work include these two things. I think that future work would be good to provide comparisons of more than just two 30-year periods. So 1970 and 2070. I think that if they had one for 2040 and 2010, it would provide more insight, especially given the sharper increase in climate change that they're predicting with the 8.5. And then one of my things I always say is that we want to look at the consequence of failure by catchment. And so this can prioritize how much to be conservative. This could be an overlay with population centers, with farming risks, even just things like elevation and other risks of other type of floods, such as ocean floods. Consequence of failure is important to have along with probability of failure. Finally, I want to take a look at the pros and cons of this paper. So in the author's opinion, one of the big pro that they see, other than just fulfilling the questions, which we've established they did, is that they saw similar results in other geographic regions in other studies, including the UK, Poland, Alpine Europe, and North America. The cons that they mentioned are that they didn't include the time varying parameters, as we mentioned in the last slide, which does limit the effectiveness of a climate analysis. And they chose to use non-controlled catchments because this allows for better analysis, but non-controlled catchments do not have as much historical data, which is really come in handy for this kind of work. In my opinion, they had some very good charts and also as well as a good simple explanation of the parameter effects on the frequency analysis method. So looking at the skewedness, the shape, the location, they had some good work there and good simple explanations of that. There was a cons. There was a sideways chart I found very irritating. Just formatting, but formatting is important for this kind of thing. In the beginning, in the method section, it says they want to decompose the variance into 3 terms, but then the results discuss decomposing into 4 terms. One of those terms is the interactions of the other 3, but it was unclear, and I think it would have been better to have it more clear from the beginning. And then finally, they didn't explain, and I'm still trying to figure out why they sometimes did a comparison to median values, and they sometimes did a comparison of average values. And why one was chosen versus the other wasn't clearly explained. But that concludes this presentation. I look forward to hearing questions, and have a good evening.